Hey y'all, so welcome to part 6 of the benchmark tutoring videos. So on these videos we're going to be talking about elements, compounds, and mixtures and the differences between each of those, plus what type of mixtures and how to figure out which one a substance is. So let's start with elements. So an easy thing about elements is they're all on the periodic table. So you will always have this on every test for academic chemistry throughout the year. It'll have the names on it and everything. So if you're ever asked, is this an element or not, it's pretty much a multiple choice test. You just have 118 choices. So you just find it and see if it's on the periodic table or not. So all known and predicted elements are listed on the periodic table. So you've got like boron, aluminum, cobalt, potassium, all sorts of stuff. It's all listed there for you. So if you're wondering, check it out. So I want you guys to freeze the video right now and just look at the periodic table. Just take about 2 minutes, 3 minutes, and just kind of look through it so you're familiar with the names. So if you hear something like calcium, you're like, that sounds familiar. Why? Oh, because it's right here, Ca, atomic number 20. So pause the video and just get familiar with your periodic table. Okay, so you should have taken a minute to have looked through the elements. So remember that each of the elements has its own symbol, and that the symbol is going to be unique for that element. So it's generally 1 or 2 letters. Actually, it's all now 2 letters. And this doesn't have, oh yeah, it does have the symbols. So if you notice like sodium, Na, so the first letter is capital, the second letter is lowercase. That way if you're ever listing more than one element, if you see 2 capital letters, you know it's 2 different elements. Because when it's 2 letters, if it's the same element, the second one is lowercase. So like lithium, Li, it's a capital L, lowercase I. Versus hydrogen here, 1 letter, capital H. Okay, so He, however, would be helium. So if there's a lowercase e followed that uppercase H, you know it's not hydrogen, it's actually helium. Okay. So a good example of what I mean by that, by the way, I'm just going to go back. Like if you see Si and they're both capitals, then it's not silicon, right? If you see a capital S and a capital I, then you've got sulfur and iodine. Versus a capital I, S and a lowercase I, that'd be silicon, Si with a lowercase I. So what's the symbol for gallium? So you have to find gallium, and this is why you want to get familiar with your periodic table. You just want to be able to look at it and kind of start finding things. In the next chapter's stuff, the next unit, we're going to go over how to read the periodic table exactly, and it's going to become more familiar. But for now, you see gallium is right here, so its symbol is Ga. All right, so what element has the symbol Hg? I want you to freeze the video until you find it, and then we'll come back and see if you got it right. All right, so did you get mercury? Mercury is what used to be used in thermometers, so if you want to remember that as my temperature rises when you see a hot guy, Hg, or hot girl, Hg, either way, your temperature rises, like thermometer goes up, right? Temperature, Hg, thermometers, mercury. Okay. What element has the symbol Se? So freeze it, find it. Did you guess selenium? Because if so, you are right. Moving on. What's the symbol for sulfur? We went over that a second ago, so hopefully you know it. Freeze. S. Sulfur. So what's a compound? Well, a compound is formed when atoms are chemically bonded together. How do you know if it's a compound? Well, if there's a chemical formula. So look over here. Water is a compound. See how it has H2O? Notice it's 2 hydrogens and 1 oxygen. Because it's in this formula together, you're saying that they are literally chemically bonded together. Water will always be H2O. It's always going to be 2 hydrogen atoms bonded to 1 oxygen atom. There's no variation there in compounds. So ammonia, that stuff that you clean with, NH3, it will always, always, always have the ratio 1 nitrogen for every 3 hydrogens. Okay, hydrogen peroxide, H2O2. So 2 hydrogens, 2 oxygens. So notice if you have water, H2O. It's a completely different thing than hydrogen peroxide, H2O2, right? So if you drink water, that's good. If you drink hydrogen peroxide, you die. Water doesn't bubble up when you put it on a cut if there's a bunch of bacteria. This will. So there's a lot of differences just with one simple element, so one atom attached to it. So if there's a chemical formula with more than one atom, so H2O, NH3, you know it's a compound because it's formed by a combination of those atoms. So here we also have CO2, so one of those major greenhouse gases you've probably heard talked about on the news, like what are the carbon dioxide emissions right now? CO2 is a compound. It has multiple atoms of elements bonded together. So keep in mind that elements are going to lose their physical properties when they're bonded together. And we saw this in the classroom when you had sodium and you put it in water and it did that. That's what I did in front of the class, if you remember. I put elemental sodium into water and it flames. Versus when you have sodium chloride, this, salt, you put sodium chloride in water, that does not happen. This is quite a different scenario than up here. So why is that happening? Well, sodium really wants to lose an electron and water is able to take it, so it has this chemical reaction. So sodium, elemental sodium, is going to react to the water. Versus sodium chloride, that sodium's already reacted, so there's no reaction. It just dissolves. It just stays salt in the water. Sodium chloride, or sodium, elemental sodium, is going to literally react with the water and make sodium hydroxide within there. So it'll react with the water, break it up, and that's what you see. So sodium reacts with water. Once sodium is already bonded to chlorine, if you put it in, there's no reaction. So it acts completely different once it's bonded. So elements have completely different characteristics once they're in a chemical bond because their electrons aren't free anymore. They're bonded with other atoms. So these electrons were free to react and we saw the reaction. The sodium in sodium chloride, the electrons are not free to react anymore, so you don't see a reaction. Also, you can think about the lab. We had iron and we had sulfur. When you just mixed it together, they still had their properties, right? The iron was still magnetic, the sulfur still looked yellow, but in the end we made iron sulfide. After it was lit, you gave it all the energy so it could actually react. This right here, this iron sulfide, is iron and sulfur once they've made that chemical bond together. They are literally, their electrons are working together to be within that compound. They are bonded, they are one. So notice this no longer has any of the yellow characteristics that sulfur has. Also, you can't see it on the screen, but if you remember, the iron sulfide didn't react to the magnet at all. The iron on its own is magnetic. So iron lost its magnetism, the property to be attracted to a magnet. Sulfur lost its color. So iron sulfide doesn't have the properties of both iron and sulfur. So here's what you did to make that happen. Also keep in mind, compounds always have a set ratio of elements. So water is always 2 hydrogen for every 1 oxygen. You get the number from this little subscript. So you look after the element symbol, so H2, so you have 2 hydrogens. O, nothing, which means 1, so you have 1 oxygen. Or here's methane, which is a little fart gas, so CH4, 1 carbon for every 4 oxygens, or 4 hydrogens. Always, 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 always. You will never change the ratio of elements within a compound, or else it's a whole new compound. So versus mixtures. So mixtures are going to be pure substances put together. So a pure substance would be an element or a compound. Mixtures is just having them hang out in the same area. So mixtures have 2 or more pure substances, which are elements or compounds, within them. So these substances are physically close, but they're not chemically bound together. And as you can see, I have a lovely, refreshing lemonade on the screen here. Why? Because lemonade is a mixture. So lemonade within it has sugar, it has citric acid, and it has water. Those are all pure substances. They are not chemically bound together. Like if you taste lemonade, you can taste the sugar, you can taste the water, you can taste the citric acid. Like they all still have their chemical properties, and you can separate them by physical means. They're put together by physical means, separated by physical means. There's no chemical reaction happening to make lemonade, right? You squeeze a lemon, you stir in some sugar. There's nothing chemically reacting here. There's no explosion, there's no fire, there's no color change. So it all keeps their properties. So since mixtures are all physically put together without adding any bonds, all mixtures can be separated physically. Right here, it's kind of hard to see in this, but this is actually a bag of cereal that's been mushed up, probably like a Special K, which has a lot of iron. And you have to have a lot of cereal to do this, but you can like smush it out and really make it a fine, fine, fine powder. And if you hold a magnet up, you can actually pull the straight up iron out of the cereal, because the cereal is just a mixture. So that iron is not chemically bound to the rest of the cereal. So once you smush it up, it's free to leave. So a physical change is something that does not change any chemical bonds. So just like pulling out iron from a mixture, which you guys did in the lab. So when you had the sand, the salt, and the iron, and you just took a magnet where like whoop, and you pulled all the iron out, you didn't have any chemical reaction. It was just iron hanging out, and then iron now hanging out over here on a magnet. So it didn't change any bonds. It was iron to begin with, it was iron at the end. That's a physical change. Physical, like it's a physical location, or maybe it's a state change, but it's in a physical change, the substances you start with are the substances you end with as well. So just pulling iron out of a mixture is a physical change because you had iron at the beginning and you have iron at the end, no chemical bond changes. So for example, removing iron, this should be from cereal, oh yes, iron in cereal by a magnet. All right, so there's two types of mixtures. The first one is a homogeneous mixture. And the prefix homo means the same. So homogeneous looks the same throughout, and it's a mixture. So it looks the same throughout. Here are some clues to look for in the wording or the description, or just to think of to know what type of mixture. So if it uses the term solution, that's always going to be a mixture. It typically means it's mixed with water, although sometimes it could be an alcohol or something. It depends, but most of the time it's mixed with water. If there's multiple options of the concentration, that's a mixture. Remember, your elements are just that. You can't change the concentration. It is an element. You can't change the concentration. A compound has a set ratio. Remember how methane was CH4? It's always 1C to 4 H's. So if there's multiple concentrations, like when you have gasoline and you can get different octane levels, well then it's not a compound because it's not a set ratio. So it has to be a mixture. And if it looks the same but there's multiple concentration options, then it's a mixture. So here's some examples. Gasoline, I just mentioned. So you have multiple concentrations. There's your clue to know that it's a mixture. So here's a picture of it, right? You're pumping. What octane do you want? 14 karat gold would be a mixture because there's multiple concentrations. You get 14 karat gold, 18 karat gold, 24 karat gold. So what that means is it's referring to the concentration of gold. So like a 24 karat gold ring is like 99% gold. Still not completely pure, but it's really, really, really gold, which is why 14 karat gold things are, maybe they're more expensive, but they're not as durable because gold is very, you can dent it easily. So that's why a lot of people go with like a 14 karat gold. Same lustrous ability, like same shininess, but it's a lot more durable. So nitrous acid solution. So that's nitric acid mixed with what? It's nitrous acid. Oh my goodness, nitrous acid. And as you can see, the other example is already going to be there. But candles. So the wax in a candle is going to be a homogeneous solution. It looks the same throughout, but there's no chemical formula. You can get multiple types of waxes, so it's a mixture. All of these look the same throughout. That's why it's a homogeneous mixture. Gasoline, if you look at the top of gasoline versus the middle versus the bottom, it's all that black liquid. It looks the same. When you go through these rings, if I look up here versus I look down here, right now you can see different reflections, but if I turn it, I'll see the same reflection in different areas. The nitrous acid solution, if you look up here and look down there, looks exactly the same. Okay, so what's the other type of mixture? It's going to be a heterogeneous mixture. So hetero means different. So it's a mixture that looks different throughout. So it looks different throughout. Here are some clues. If you can see multiple phases. So as soon as you see multiple phases, you know that it looks different. Anything living is a heterogeneous mixture. This is Ralphie. Ralphie is a heterogeneous mixture. If you look at him, he doesn't look the same throughout, right? His nose is going to be different than his fur, that's different than his organs. So it's a mixture, it's a bunch of different pure stuff all put together. Anything living is a heterogeneous mixture. All right, some examples. Fruit salad is going to be a heterogeneous mixture. If you look at it, it looks different throughout. Like you've got strawberries, you've got blueberries, grapes. Those are each called a different phase. It looks different. A phone, it looks different. This cord that feels different than the hard plastic here on the actual phone part, which feels different than the rubber buttons, which is different from the screen here. Rocks in oil. So oil would be a pure substance. Your rocks, depending on what they are, might be a pure substance, but this doesn't matter because it's definitely a mixture. So all of these also can be separated by physical means, right? You can pour out the oil. You can pick up one of the rocks. So, all right, here is also a chart that kind of goes over all of them. So if you could please freeze the video and take a minute and just read through this. This kind of separates things and lets you look at the differences. And then talk to your teacher if you have any questions about the differences in each of these before we go further. Okay, so let's go through a few things and see if you can figure out what they are before we go into the let's try on your own. I've got some sample items here on my desk. So first, a little Campbell's soup plug. What do you think this is? So this soup, the country-style beef noodle, well, is it an element? Do you see Campbell's home-style, country-style beef noodle on your periodic table? Probably not. Is it a compound? Is it a set ratio of elements? No. If you pour it, you might get more noodles in one bowl, less noodles in the other. So it's not a compound. Is it a mixture? Well, yeah, it's literally stuff mixed together. So is it a homogeneous mixture or heterogeneous? Well, does this look the same throughout? If we look at this picture, does it look the same throughout? No, you've got some chunks of beef, some noodles, some broth, so it doesn't look the same, heterogeneous. How about inside here, we have salt, which has the formula NaCl, sodium chloride. So you've got sodium that's on the periodic table and chlorine that's on the periodic table. It's in a set quantity, 1 sodium to 1 chlorine, so it's a compound. Okay, next thing is ibuprofen. So this is a little NSAID, fever reducer, ache reducer, etc. I'm talking about literally just the ibuprofen part. This is kind of a tricky one. So not the actual pill, so I'm not talking about the coating on the outside, but literally the ibuprofen chemical inside. What do you think? So that is going to be a compound. There is a specific formula to make ibuprofen. Let's see if I can find it on here. Well, it says active ingredient ibuprofen. You can also look at the ingredients. That's sometimes fun, but there's a chemical formula for that. How about mousse? Maybe you've used this, maybe you haven't. A little Aussie mousse. So does it say mousse on your periodic table? No. So it's not an element. Is it a compound? Maybe. So then you have to think, well, is there a set ratio of substances in every single mousse out there? No, there's differences. So you can get like a stronghold mousse or one that has scents in it. So that's going to tell you that it's a mixture. And mousse looks the same throughout, so it's homogeneous mixture. Okay, next thing, sugar. This is how I keep my sugar at my house. So sugar is C6H12O6. So if it's a formula in it, compound. Okay, how about in here? This is aluminum foil. This is just aluminum. Is it on the periodic table? It is. So this is an element. This is the element Al, aluminum. Next thing I have, I've got some tap water that I was drinking. So not talking about the outside, but the tap water. Tap water is water, but it's not pure. There's other stuff put into it. So it's similar to a compound. You might think it is a compound, but it's actually not. We put like fluorine and stuff to help your teeth in tap water. So it is going to be a homogeneous mixture. Let's see, what else did I grab? How about, oh, I grabbed a battery. So if you have a battery right here, so this is a battery. So does it say battery on your periodic table? No. So it's not an element. Does it say Duracell on your periodic table? No. Is it a compound? Well, is this one thing throughout? No. You can see lots of stuff. There's multiple phases. If you ever see multiple phases, you can quickly go to heterogeneous mixture. See how this part looks different from here, which looks different from here. This is a heterogeneous mixture. Inside of this are pure substances. Like you might hear a lithium battery. You don't want to take that on an airplane. You're not supposed to bring lithium batteries on an airplane or ship it in packages. Lithium is an element. So the mixtures have pure substances in it, but they themselves are not a pure substance. They are a mixture. I also have plant food. So you might be wondering, because these sticks, each of them, yeah, it does look the same throughout. So I'm going to pull one out so you can see it, this plant food right here. Maybe it's a compound, I don't know. So you're going to go to the label here, and you're going to see, oh, well, it's got nitrogen, it's got magnesium, it's got sulfur, it's got boron. Interesting. So it has a bunch of different elements in it. So then you have to think, is it a compound or a homogeneous mixture? Well, this is the Miracle-Gro version. I could get another brand that has a different concentration of things in it. So you know that this is not a chemical compound. It is indeed a mixture. Milk. You can get it in 2%, you can get it in 1%, you can get it organic, you can get it not organic. There are multiple options of what kind of milk, which gives you a clue that it's not a set ratio of substances. So if it's not set, it has to be a mixture. Homogeneous, because it looks the same throughout, mixture. Think about it. There's protein in it, there's calcium, there's water, there's all sorts of stuff in your milk. So it's a mixture of all those things. All right, so from here, let's go into, now it's your turn. So you have all this listed on your follow along sheet. So you are going to identify if each of these is an element, a compound, a homogeneous mixture, or a heterogeneous mixture. So go ahead and freeze your video, and when you come back, we're going to go over all the answers. Don't forget to freeze your video. Okay. All right, so you should be back. Let's go through the answers. So pizza, well, does it look the same throughout? No, it has different phases. You've got the bread, the sauce, the cheese. So automatically, if it looks different throughout, that's a heterogeneous mixture. A brownie, does it look the same throughout? Does it not look the same throughout? Well, is it on the periodic table? So this is going to be a homogeneous mixture. Think about it. It looks the same throughout. So you've got element, compound, homogeneous mixture. Those are your three options. It doesn't say brownie on the periodic table, so cut that one. So you're between compound and mixture. So compound or homogeneous mixture. Well, brownies can have multiple concentrations. There's not a set way to make brownies. I have a secret recipe that maybe someday I'll bring in brownies if classes are really good. My friend's grandma gave it to me, but that's not used by everybody. So different ways to make it. How about carbon? Well, carbon is like what you write with in your pencils, or it can be a diamond is made out of carbon, but it's on the periodic table, so we know it's an element. A remote control, multiple phases. The rubber buttons look different than the plastic, which is different from the batteries, which is different from the wires. So there's multiple phases. It's automatically heterogeneous mixture. Sodium, it's on the periodic table. If you're looking at the periodic table, look to the left if you weren't able to find it. Na, sodium, element. Glucose, that's that sugar I showed you earlier, C6H12O6. Glucose is what you make most of your food into in your body to do cellular respiration. It is a compound. You know that because there is a formula. So if you don't remember glucose from bio, at least you know, oh, there's a chemical formula. I see more than one element here, so that means they are bonded together. It's a compound. Silver. Silver is on the periodic table. Ag, silver, element. Amphetamine, that is one of the main parts of, I think, Ritalin? I'd have to check on that. But there is a formula, C9H13N, so amphetamines would be a compound. Tungsten. This is Mr. Klein's favorite element if you had him as a teacher. Tungsten is on the periodic table. The symbol is W, so it's an element. Sodium hydroxide solution. So when you put that sodium in water, remember it lit on fire, the sodium reacted with the water, released some hydrogen, and made some sodium hydroxide, but there was still some water left over. I didn't use enough sodium to react with all of the water, so it wouldn't be pure. It would actually be considered a solution because it was mixed with water. So since I just said the word mix, that kind of gives you a clue. It's a mixture. It looks the same throughout, so it's a homogeneous mixture. Anytime you see the word solution, homogeneous mixture. All right, if you have any questions on any of those, please ask your teacher before you move on so you get all your questions answered and you can get them all right when you do the benchmark retake. Okay, see you later.